Right, so here's example 10 for proofs. So we need to state whether the statements, 5 statements, are true or false, and provide a proof for those statements which are true, or a counterexample for those statements which are false. So counterexamples are usually used to disprove a statement or to prove that a statement is false. So for algebraic statements, we can provide a counterexample for substituting a value for that variable and show that it is false. Because if an algebraic statement is only false for just like exactly one false input, then game over. That statement is at whole false. Alright, for part A, for every integer n, we have n minus 2021 an integer. And it's not hard to see a counterexample. Let's just say when n is equal to 2. When n is equal to 2, we have 2 minus 2021 over 2. However, notice that the numerator of this expression or fraction is an odd number, and therefore this is not an integer. So therefore this statement is false. And in fact, this statement is only true if and only if n is an odd integer, not necessarily negative, non-negative, something like that. For part B, if x is divisible by 27, then it must be divisible by 3. Let's just prove that this statement is true. So if x is divisible by 27, or in other words 27 divides x, therefore x could be expressed as 27 times k for some random integer k. Then it must be divisible by 3. Then we wish to show that x could be expressible as 3 times another integer, something like that. Now it's pretty simple because we can just factor out a 3 out of this expression, and we have 9k inside. And we know that this inside is an integer, and therefore our variable here is divisible by 3. So hence the statement is proven to be true. And even if you try to find a counterexample, you cannot prove that this statement is false. Right, for part C, the converse of B is also true. So the converse of a statement is that when you flip two parts of the statement. So here, the converse is if x is divisible by 3, then it must be divisible by 27. Now, this statement is false, and we can prove this by providing a counterexample. Let's just say 6, because 6 is divisible by 3, or 3 divides 6. Notice here that 6 is not divisible by 27, and this statement is false. So this statement is false. And I accidentally erased a here, and we have proven that it is also false. For part D, any odd natural number greater than 1 could be expressed as the sum of two consecutive natural numbers. Alright, so let's say the smallest number that is being summed up to be an odd natural number be n. Therefore, its consecutive natural number, or its partner, will be n plus 1. Therefore, its sum will be n plus 1, or just simply 2n plus 1. Now notice that this is the expression of an odd number right here. So therefore this statement is proven to be true. Now notice you can plug in some values for n. Let's say just take n is equal to 1, therefore the sum is 3. Coming back to our assumptions, the two consecutive natural numbers will be 1 and 2. Checking for 5, we have 2 and 3, and so on. Now for part E, the final statement. Any integer could be expressed as a sum of 4 consecutive integers, not necessarily non-negative. Again, this statement could be proven false by providing a counterexample as shown. We can take our integer value to be 7. Now notice no matter how hard you try, 7 cannot be expressed as the sum of 4 consecutive integers. Because notice that we have 0 plus 1 plus 2 plus 3, which are 4 consecutive integers being equal to 6. And then we have the next integer that is expressible as the sum of 4 consecutive integers being 1 plus 2 plus 3 plus 4, which is 10. And notice that there is a gap between here. That means the numbers 7, 8, and 9 cannot be expressed as the sum of 4 consecutive integers. So therefore, this statement is proven to be false since we have provided a counter example. And this ends this video.